Hello, class. This is Mr. Hart, and in this podcast, we want to start the radiation chapter of our textbook. And you probably heard the term radiation, or may even have an idea about what radiation is, but we want to answer for sure what exactly is radiation. Okay. Now, you may have thought of radiation as something that makes something glow green, or gives off a strange color, or is kind of some weird ooze, or whatever you may think it is. Okay, you may have thought it gives people superpowers or turns you into an X-Men or something like that, but unfortunately, this is not the case. Okay, so radiation isn't something that's strange or berserk or mysterious. Okay, it actually has a really simple definition. And so, if we look at the actual definition of radiation at the most basic level, it's just the emission of particles or energy. That's it. That's all it is. Radiation is just emitting a particle or energy, basically shooting out particles or energy from an atom. That's all radiation is. Okay? So something that is radioactive in that case is just a substance or material that frequently emits radiation. Okay? So radioactive material is something that's, consistently shooting out particles or energy. That's all it is. Okay? And then we have another term which we'll look at more in a second, which is a radioisotope. And that's an unstable atom configuration that will emit radiation as well. And so, again, I kind of want to just reemphasize that radiation in itself is just not that dangerous or scary or mystic or anything like that. It's just shooting out particles, shooting out energy. And for the most part, it's really quite harmless unless you're looking at the very large scale. If you're using large amounts of energy and shooting out large amounts of particles, that's when it starts to become a problem. But in its most basic form, it's really not that big of an issue. Okay, let's look at this term, radioisotope. This is a very important term when it comes to radiation. So before we look at radioisotopes, let's just look at isotope. So you probably remember from like 8th grade science or another chemistry class that an isotope is just when you have different numbers of neutrons in an atom. Okay, so let's say we're taking hydrogen, for example. And hydrogen usually just has one proton and one electron. Okay, but it also can have one proton, one neutron, and an electron, and it can also have one proton and two neutrons and electrons. Okay, all three of these configurations are considered hydrogen. Okay, this is hydrogen, this is hydrogen, this is hydrogen. They behave like hydrogen, they react chemically like hydrogen. They have all the properties of hydrogen except they just have a different number of neutrons. Okay, so we call these isotopes. We give them names like deuterium and tritium for hydrogen's case. Okay, other atoms have other isotopes that they can have. Okay, again, they behave the exact same way chemically, but they have a different number of neutrons in the nucleus. So a radioisotope is one of these configurations which isn't stable. So for example, let's say I try to add another neutron to this configuration. Okay, so I got another neutron. And it turns out this atom wouldn't be stable with this neutron because of the different forces inside of the nucleus. And it wouldn't be able to stay there. It wouldn't be able to exist in this atom. So if there was a hydrogen molecule that had 3 neutrons and 1 proton, it would be unstable. It'd be a radioisotope. What it's going to do is eventually it's going to say, hey, this guy doesn't fit, so we're going to kick him out and we're going to emit him as a particle. And so instead of having 3 neutrons now, it's just going to get rid of that guy and send him outside and, just shoot him off as radiation, okay, in order to become more stable. So these radioisotopes are huge when it comes to radiation because that's really the cause of all the radiation is unstable isotopes, unstable atoms. And so we have this big idea for radiation, okay, and it's this, that atoms that are radioactive will emit particles and energy in order to become more stable. Okay, these radioisotopes don't like the configuration they're in. They don't like the number of neutrons they have or the number of protons or something about the configuration. And in order to become stable, they're going to try and get rid of something. Okay, all radiation comes from this removing something from the atom in order to become stable. Okay, let's look at carbon-14, for example. Carbon-14, if you look at its configurations, if you look at the protons and the neutrons, carbon-14 is going to have 6 protons and 8 neutrons. Okay, this isn't a stable configuration on that scale. It's having 6 protons and 8 neutrons doesn't work out. They're not the same. Okay, and so in order to make it the same, they're actually going to turn one of these neutrons into a proton. Okay, in this picture you'll see that they emit an electron that turns a neutron into a proton. And so instead of having 6 and 8, you get 7 and 7, which is what nitrogen 14 is. Okay, so this is another example. Carbon 14 doesn't like the amount of charge that it has. It doesn't like the number of protons compared to neutrons. So it's going to emit a beta particle is what it's called, or an electron basically, in order to become stable. Nitrogen 14 down here. Okay, so this is a nice configuration. This is not. And so again, it's just going to emit something. It's going to emit radiation in order to become stable. Okay? So that's the very basic idea of what radiation is. Any radiation you see comes from this at some point. Okay? So let's get more into the details though. So there's different ways that you can become more stable. Okay? There's different types of radiation. So some atoms will emit alpha radiation, which is the emission of a helium nucleus, which is 2 protons and 2 neutrons. Okay? So basically just a big, bunch of, particles. Okay, and this is generally to decrease the size of the atom. So if you have, for example, uranium-238, which has 238 protons and neutrons in it, okay, that's a big atom. It doesn't like having that many particles in the nucleus, so it's going to emit alpha radiation and get rid of some of those protons and neutrons. Okay, you can have beta radiation, which is what we looked at just barely with carbon-14. So this is an emission of an electron. This can decrease the charge of the atom. It can change a neutron to a proton. And so it usually deals with that type of configuration where you're changing some of the charges inside the atom. Okay. We also have gamma radiation, which often occurs alongside alpha and beta radiation. That's the emission of just pure energy in the form of electromagnetic waves. Okay. And this decreases what I call the motion of the atom, basically how much the atom is moving around. It's not exactly that way, but we can kind of think of it like that. It has to do a lot with the orbitals of the electron, and when you take chemistry, you'll learn more about that. But for right now, we just want to realize that there's, the electrons are going around different orbitals, the particles inside the nucleus are moving, and so in order to decrease some of this motion, some of this chaos, it's going to emit this energy so it can kind of calm down. Okay. It's kind of like almost like a cooling for the atom. It cools down the atom by releasing some of the energy. Okay. And so again, that's not exactly what it is, but that's how we can think of it for this case. And so this energy kind of decreases the chaos of the atom and makes it become more stable. And again, it usually doesn't do this by itself. Usually it's alongside alpha and beta radiation. Okay. All right. And so in case you're wondering, the way they got their names, if you look at alpha, beta, and gamma, they're just the first 3 letters of the Greek alphabet. And so it was actually kind of a lazy naming system. They just said, hey, this is the first one we found, so we'll call this alpha. Well, this is the second one we found, so we'll call it beta. This is the third one, so we'll call it gamma. It's just A, B, C, basically. And so A radiation, B radiation, C radiation. Okay. And in class, we watched a video that kind of reviews all these concepts. We also looked at a simulation that shows how this decay is kind of spontaneous and random, just depending on when the atom becomes unstable enough to emit the radiation. Okay. Let's talk about radiation absorption. Okay, so we have these different types of radiation, and it can be kind of confusing sometimes when we hear about radiation on the news or in a report, and what type of radiation are they talking about? Are they talking about alpha? Are they talking about beta? Are they talking about gamma? Sometimes they state it, sometimes they don't. Okay, but let's look at how we can kind of tell which type of radiation they're talking about based on absorption. Okay, so alpha radiation, because it's particles, okay, just protons and neutrons, subatomic particles, it's very easy to absorb. Something like your hand or a piece of paper will absorb alpha radiation. Okay, and it's very dangerous to absorb alpha radiation because if you look at an atom, let's say you have a bunch of oxygen. Okay, and oxygen has 8 protons. Okay, and then you look at an atom like neon. Okay, which has 10 protons. Okay, if the oxygen in the air is absorbing alpha radiation, or the oxygen in your hand or wherever it may be is absorbing alpha radiation, that alpha radiation comes with 2 protons. So no longer will you have oxygen, you actually will have neon, okay, which can add for some strange effects, right? Your chemistry is actually changing. So if you have alpha radiation absorbed by your hand, it's not going to be very good. It usually causes what looks like a burn, basically. And it's changing the chemistry, it's changing the atoms and the chemicals, and so it's not a pleasant thing to absorb alpha radiation. But the nice thing is it is easy to absorb. So rather than using something like your hand, you can just use a piece of paper or some cloth or something like that, and it will absorb the radiation for you. So alpha radiation is very, very dangerous because it can change so many things, but it's very easy to absorb, which is nice. And so generally speaking, if you just see a report and it mentions radiation, they're usually not talking about alpha radiation because it gets absorbed so quickly, generally speaking. The next type is beta radiation. And beta radiation, again, is just an electron, basically. So anything that electricity flows through, a beta particle can flow through. So generally it will flow through your hand because electricity can go through your hand. Usually you need something that is a nice metal to absorb the electricity, absorb the beta particle. And so any type of metal generally will absorb that energy. And again, it's not very dangerous because it's just like an electric charge. And so it's not going to do much damage. It can make electrical storms sometimes and things like that. It has been known to knock out power grids and other things in some cases. And then the last one is gamma radiation, which is usually the one they're talking about in the news when they mention radiation, because it just travels through everything. Okay, it's really hard to prevent gamma radiation. It travels through your hand. It travels through aluminum. You need about 3 or 4 feet of lead to really stop gamma radiation in its tracks, because it's just energy that's moving through particles. If you have an atom in your hand, for example, that is hit by gamma radiation, it may not necessarily absorb that radiation or only absorb a very small amount, because the energy isn't just going to transfer all into that one atom. It's going to just pass right through it, which is why it isn't dangerous on a small scale because it just passes through everything. But on a very large scale, gamma radiation can be a problem because it goes through so many things and can be absorbed by so many things in large quantities. Okay. So again, alpha radiation is probably the most dangerous, but it's so easy to block that it usually is not a concern. Whereas gamma radiation in very large quantities can be quite troublesome because it goes through so many things. It's hard to prevent. Okay. And the last thing we want to talk about for this podcast is detecting radiation. Okay, and we use a machine that we call a Geiger counter. It's kind of a weird name, but it was invented by a man named Geiger, and it's this box over here with this microphone-looking thing sticking out the top, and it's kind of looks like a metal detector, and it works in kind of a similar way. You just point this microphone basically towards your source, and this machine will read out to you or even make little tones and beeps saying each time that it receives radiation and the amount of radiation that's it receiving. Okay, and so you may be getting a lot of radiation or a little, and it'll indicate on this little device right here that how much radiation you are receiving from that source. This is an older one, probably from the 60s or 70s. Nowadays, we have much more advanced ones that are digital and they're much smaller, so you can hold them in your hand rather than have to carry around this big box. But the principle is the same. They just read out how many, or how much radiation you are receiving. Okay. So that's all we want to cover for this podcast. Hopefully that gives you a nice basic foundation of what radiation really is and how we kind of detect it and measure it and analyze it. Next time, or next podcast, we're going to look at the uses of radiation and some of the dangers of radiation and how we can prevent it and control it. But hopefully that all makes sense. Let me know if you have any questions, and thank you for watching.